Hello, and welcome to Totally Not a Ripoff of Crash Course, Episode 3. I'm your host, Rahul. Today, we're moving past American history, and we're leaving it with a bang. This time, we're talking about fireworks. Fireworks originated in ancient China, but that's not our focus. We're focused on the science behind fireworks, specifically the chemistry of fireworks. Let's begin. Play the intro now. Woohoo! Intro time! So I was gonna play Katy Perry's Firework, but I can't because I'm gonna get copyrighted, and I'm poor, so that doesn't work. So this is the excuse you have for an intro. This is also a great way to stall time. But now that I mentioned that, I gotta keep moving, or else I'll fail. Let's go to the video. To start, let's look at exactly what a firework is. A firework is a device used primarily for entertainment, producing loud sounds and bright lights for celebration. But the big question is, what exactly makes up a firework, and how does it produce all these big sounds and big lights? Well, let's get to the animation. This is a drawing of a firework. The firework has 5 parts: the nose cone, the effect, the charge, the fuse, and the stick. Let's start with the stick. The stick keeps the direction of the firework. Without the stick, if the firework was lit, it would go off in random directions, and obviously that is very, very unsafe. It also helps the organizer position the effects accurately. I mean, the stick is essentially just a stick, and it is one of the most practical, but also the most boring of the parts of a firework. This is the fuse. The fuse lights up the rest of the firework. It also allows for the timing of the individual fireworks effects. When the operator actually launches the firework, what they do is they just press a button and then a wire will send an electrical signal to the fuse and ignite it, which will also in turn ignite the other parts, aka the charge, the nose cone, and the effect, not in that order obviously. Now let's get to the charge. The charge is where the exploding really happens. The charge is a crude explosion that propels the effects of part of the firework a lot higher. It is made of tightly packed gunpowder, specifically black powder. Now I make this distinction because gunpowder refers to more things than just the black powder that we all kind of associate with. Gunpowder nowadays, especially in modern weaponry, is a lot more powerful than the black powder that we see in a firework. But the explosion in a firework is nothing to be laughed at. The explosion is so powerful that it will propel the effect and the nose cone, the other 2 parts of the firework, up faster than a jet fighter. Now that we mentioned gunpowder, let's talk a little bit about it. Gunpowder is made of 3 different parts. Now obviously the question arises, what are these 3 different parts? So the 3 different parts of gunpowder are... What? Wait, why am I being censored? Alright, this is so stupid. You can look this up on Wikipedia. Who's censoring me even? I don't even know what... Alright, no, it's fine, let's just move this out of the way. Just push this out of the way. Alright, there's too much effort. 1 second, let me just... There we go. Alright, 3, 2, fire in the hole! I should have said that before. 2, 1... Boom. Much better. So let's move past whatever that was, and let's get into exactly what gunpowder is comprised of. Gunpowder is comprised of 3 different substances. It is comprised of 10% sulfur, which sulfur is used to lower the ignition of, the ignition temperature of the entire reaction. So you can actually light it and set it on fire without having to go to just absolutely ridiculous temperatures. Next, we have 75% of gunpowder being composed of potassium nitrate. Potassium nitrate's use, well, we'll get into that a little bit later. But the last 15% is made up of charcoal. Charcoal acts as the sort of fuel of the reaction. To model saltpeter or potassium nitrates, sort of use, let's look at this equation, this chemical equation. Very scary, I know. Uh, Here we have potassium nitrate, carbon, sulfur. We have which produces potassium carbonate, potassium sulfate, carbon dioxide, and nitrogen gas. This looks pretty uninteresting when you just first look at it, but trust me, it's pretty, kind of interesting. Potassium nitrate's use is, well, it is an oxidizing agent to carbon and sulfur. To illustrate this, let's look at the oxidation numbers of each element in either side of the equation. We see on either side potassium's oxidation number does not change, and that's to be expected. We see that oxygen's number is not really changed at all. Carbon's number is changed. Carbon, we see it being oxidized, +4 from +0 to 0. Sulfur to +6. It's being oxidized. Now, what's oxidizing it? KNO3. And obviously, when something is oxidized, something's got to be reduced. And what's being reduced? Nitrogen. You see, nitrogen has +5, and it turns into gas. And whenever you have N2, or just like a single element there, well, the oxidation number is 0. So there's our oxidation and reduction reaction. So this is all well and good. And also, potassium nitrate also supplies the oxygen for the reaction completely, which is fantastic, very useful. But now this is great, but so what? I mean, I didn't really get to why it explodes, did I? Well, this reaction happens, first of all, very quickly. I think that's something that we all already know, just based on just prior knowledge. But why? Well, let's look at some numbers. Notice the gases, CO2 and nitrogen gas. What's special about them? No, it's not some chemical property, or I don't think it is a chemical property. Just kidding. It's the moles. It's the amount of moles. A lot of gas is produced in this reaction. And if it's a very fast reaction, a lot of gas is produced in a very fast period of time. It goes boom. Because, the gas is produced and... Did I just make an exploding noise on my own presentation? I did. I'm full of surprises today. And so we have 11 moles of gas and 5 moles of solid. So I think it's easy to sort of picture why this thing explodes. You get a lot of gas very quickly, and since you got carbon here, you got the charcoal, you have the fuel, which means you got the fire, and the fire means everything's gonna be hot, and that's why, if you stand near gunpowder when it explodes, which I do not recommend, it's gonna hurt. It's very hot. Like, what do you think? So let's get to the fourth part of a firework. A firework's fourth part is the effect. The part where, the stuff inside generates the sparkly colors that you see in fireworks. So what does the effect, I would call it, do? It makes the actual display. Whatever's stored inside, the stuff that's stored inside this thing creates all the pretty colors and all the fancy looking things, and it's timed so that the effect goes off when it's safely high enough in the air. So what you have to realize here is that when a firework explodes, you got a lot of very hot material on you, very, very hot. So you want to give it enough time to when it falls down, it's cool enough so that it doesn't hurt anybody or cause any fires. It's made up of loosely packed clay balls called stars. These are, if I may use the terrible pun, the stars of the show. These contain the colorful effects that we'll get into a little later of the firework. It also has some gunpowder in it as well because you need something to like light the stars to actually create the pretty colors. But well, the stars are the main part of it. And there are many different ways to sort of pack this portion of the firework so that it creates different effects, different colors, etc., etc. So we already established that sort of fireworks explode and they propel very high and it's just fantastic looking. You get all these, nice looking explosions and stuff, but we never really established what produces these colors. The colors are produced by metals inside the clay stars. Right in the last sort of animation thing that you saw, you saw the effects sort of part of the firework. And those effects have little clay stars in them. Those clay stars have metal in them. Metal compounds, obviously, because if you just had the metal, then the metal would like literally explode on itself. But it had metal in it. That metal is very, very important. And the reason why the metal will give off color is because we already established that the entire environment, when you will light gunpowder near these stars, is going to be really hot. You're going to get a lot of heat to the metal. And when you get a lot of heat to the metal, the electron will get excited. It'll want to jump up to the higher shells. And that's exactly what it does. In doing that, it gives off light. By absorbing the energy, it will give off light in wavelengths that, well, we can see. So I could illustrate this with more really bad animations, but I think it's best that we show you some experiments that the group did to actually create colorful flames. Let's look. So in our little experiment, we decided to test 5 elements. We decided to test sodium. We decided to test calcium. I would apologize for my handwriting, but, well, no. Strontium, magnesium, and copper. This is not in any particular order. I just don't. This is the order I remember them in, oddly enough. So, here we have each element had its own color that it produced. Some looked a little bit similar than others, but they were all distinct colors. At least distinct enough for us to tell. Here we have copper. Copper creates a blue-green color. You see here, there's blue. A lot of blue forms at the base, but as you go up and up and up, you get green. Here, you see a yellow-orange color. The yellow-orange color comes from calcium. Calcium produces this interesting yellow-orange color. Very similar to calcium, sodium produces a purely orange color. Wow, that's a terrible way to write sodium. Let's just quickly fix that. Sodium produces orange. A very pure orange, I would say. There's really not a whole lot of difference between the inside color and the outside color. Strontium produces red. This very bright red it produces. And lastly, magnesium actually produces a very magenta color. You don't see it very much at the center, but if you look where I just circled, you can see a little bit, just a tiny bit of magenta. But that's our magnesium. So this essentially answers the question, well, what would these different metals produce? each of these metals were actually put with chlorides, so we got their metal chlorides. And it also proves that, well, the chlorides don't really matter. The chlorides didn't change anything because we kept them consistent. It was the metals that changed something. Let's move on to the last part of the firework. Next up, we have the nose cone. And this is actually our last part of this firework. The nose cone is not really something that contains gunpowder and explodes, or at least it's not what its primary purpose is. The nose cone is something to make the entire firework more aerodynamic. So when you launch something up in the air, obviously you're going to have the air kind of pushing back at it, called air resistance. But to combat that, you would essentially shape the tip of your firework to make it so that the air kind of goes around it and doesn't resist the upward force of the firework as much. Many of these fireworks have blunt ends. I chose a pointy end because I thought it looked better. But the pointier ends are more aerodynamic to make the firework go a lot faster up, because you see, with less air resistance, the firework's gonna go higher up. So, hope you guys learned a lot about fireworks. Fireworks are definitely one of those things that you don't really think you'd ever, well, think about. You know, how do they work? You just kind of go with them on the 4th of July or whatever and see them explode, and it somehow entertains you. But, nevertheless, hope you guys learned something. And I will see you in the next episode if anybody actually watches this show. Except, obviously, the AP Chem class, but, like, yeah. Bye. Look, it's 3 o'clock in the morning, literally, and probably when this thing actually uploads, it's gonna be 4 in the morning. Why am I doing this to myself? That's a very good question, and honestly, I'm not sure. I got like a math test tomorrow, and like a Spanish thing too. What am I doing? Like, I should be studying. Just kidding. I'm not studying for Spanish. I don't even know what's going on. Oh god. Oh god. Considering this is on my YouTube channel, like, favorite, subscribe for new videos that never come out ever. Like, yeah. By the way, for anyone who doesn't know, this is an actual series. Totally not a ripoff of Crash Course. Is a series on my channel that I've done 3 episodes for. Though I'd advise you don't go to the other episodes. They're pretty bad. I don't know, the first one's pretty bad. Second one's okay, I guess. This one's probably one of my best. Though that's not saying much, is it? Alright, this is going on too long. I'm stalling. Bye.